All right. Good morning, everybody. Welcome back. So let's continue today talking about thermochemistry. Okay, so the goal here is first to understand the flow of energy from system to neighborhood. So that's the first goal of thermochemistry. And then from there, we must be able to determine the value of the energy produced or absorbed by a reaction. Okay, so let's see where we left off on Monday. Okay, so that was the point we stopped. So I showed you how to draw a simplified energy diagram, and reading the diagram determine if the reaction is endothermic or exothermic. And also, if a energy diagram is given, you have to be able to read the energy diagram and classify the reaction in endothermic or exothermic. So the first example here was for an endothermic reaction. So we know that this reaction is endothermic because delta H is positive. Okay, so the reaction at the end needs energy to progress. The second example here that we are going to start tackling today shows hydrogen reacting with carbon monoxide, and the only product of this reaction is methanol. For the delta H of this reaction, we see here a negative value. That alone indicates that this reaction is exothermic. So now let's draw the energy diagram for this reaction. Again, any simplified energy diagram has a vertical axis that is energy, and we are going to represent the energy level for reagents and products by vertical lines. Okay, so if the reaction is exothermic, that means the energy of the reagents, hydrogen and carbon monoxide, is higher than the energy of the product, in this case, methanol. And the reaction goes from higher energy to lower energy. That means energy is being released from the system to the neighborhood. Okay? So that will cause a increase in the temperature of the neighborhood of the system. In most of the cases, your reaction flask. And attention here, the delta H for the reaction is always the difference between the enthalpy of products minus the enthalpy of reagents. For this specific reaction, we have the delta H, and it's minus 128.33 kilojoules. Okay, so that's how you draw simplified energy diagrams for endothermic and exothermic reactions. Okay, so let's move on here to my other screen. Okay, let's return to the PowerPoint. Okay, so now let's talk a little bit about some examples. You did something similar already yesterday during the discussion section. Uh, let's talk about the physical state transformations. So if we start from the solid state and we need to move to the liquid state or to the gas state. So every time you have a solid, you need to provide energy to melt the solid. And the same thing from liquid to gas, you need to provide energy to move from the liquid state to the gas state. Just by the fact that you need to provide energy to move from left to right, that means those transformations are all endothermic. Okay, so they absorb energy from the neighborhood to happen. Always, when you move from one direction all the way to the other extreme, and these transformations are endothermic, when you move to the opposite direction, you are just going to change the sign. That means from vapor to liquid to solid, the transformations are all exothermic. Okay, so this is valid for any reaction. If you move in the opposite direction, the delta H value is the same, but the sign is changed. So that's why if acetone touches your skin, you feel a cold sensation. Acetone has a very low boiling point. When it touches your skin, is going to move from the liquid state to the gas state. This transformation needs energy to happen. The energy is going to be absorbed from your skin. And that's why you feel a cold sensation. And that's one of the mechanisms that your body uses to regulate temperature. So when you sweat, that means you are overheating your body. So what your body does is to release water in the liquid state. The water in the liquid state is going to move slowly to the gas state. This is an endothermic transformation, and to happen, it will need to absorb energy from your body. Okay? Therefore, it will have the intention to cool down your temperature. We can also correlate the value of the delta H of the physical transformation with boiling point or melting point, for example. Lower the amount of energy needed for the transformation, that will reflect in a lower boiling point or melting point. So let's compare here four chemical compounds: helium, acetone, ethanol, and water. And let's compare the delta H for the vaporization process. So therefore, we are looking for the transformation between liquid and vapor. You can see here that helium needs the lowest amount of energy for moving to liquid, from liquid to vapor, followed by acetone, ethanol, and then water. Therefore, the boiling point for helium is going to be the lowest one in this series, because it really needs a very tiny amount of energy for the transformation to happen. And that will be followed by acetone, ethanol, and then the highest boiling point will be for the water because it needs more energy to happen, therefore higher temperature. And always remember, if the transformation from liquid to vapor has a positive delta H, when we flip the direction from vapor to liquid, the number is going to be the same, but the sign is going to be flipped. So therefore, for water, delta H of vaporization is plus 44. If we change the direction, delta H of condensation is going to be minus 44. All right, moving on. Okay, so now we are going to start investigating what are the methods to determine experimentally the delta H of a chemical reaction. Sometimes it is very hard to reproduce a chemical reaction in the lab, sometimes because of the temperature is too high or the reagents are too expensive. However, breaking down the reaction in small parts is more doable, and we can combine all the small steps to figure out the big picture. So we are going to start talking about the Hess's law. Hess's law takes advantage of the fact that energy is a state function. What does that mean? Any state function means that only the initial and final state matters. When we are measuring the delta H, we are always looking for the final enthalpy minus the initial enthalpy. It does not matter the intermediate steps that we are taking to get from start to finish. So imagine here the following analogy. We have here a mountain, and we meet at the base of the mountain, for example, at this spot right here, and we should to go for a hike and meet at this point of the mountain. Okay, so start and finish, enthalpy of the reagents and enthalpy of the products. Some of you take the straight shot all the way to the meeting point. Some of you may go to this point, stop a little bit, and approach the end towards this side. Some of you go all the way to the top and then go back and meet everybody here at the meeting point. So that's the same with chemical reactions. A reaction can shoot directly to the products or go to intermediate states and get to the same product. It doesn't matter the way you got to the products, it only matters the initial and final state. So that means the overall reaction enthalpy is the sum of the reaction enthalpies of the steps in which the reaction can be divided. Okay, so with the Hess's law, we are going to break down very complex chemical reactions in small steps, and adding up all the small steps, we are going to find the enthalpy of the more complex reaction. So let me show you an example here. Switch to my other screen. Okay, so imagine here that we have a problem to measure the enthalpy for the following transformation. Water starting in the solid state and moving directly to the gas state. For some reason that doesn't matter right now, we cannot measure the enthalpy of this single step. So I'm going to draw the energy diagram for the reaction that we are having a problem, which is water in the solid state, going all the way to water in the gas state. Okay, so therefore, the name of this physical transformation is sublimation. And our goal here is to measure the delta H of this transformation. I know that this transformation is endothermic because we are moving from solid state to the gas state, therefore from left to right in the physical state chart. It must be endothermic. The good thing about this transformation is that we can easily measure the enthalpy of the water going from solid state to liquid state, and then from liquid to gas. So we have those numbers here, and there is no problem to measure them. Okay, so see that the problem reaction has a starting point and an ending point. The intermediate reactions are going to break down this whole pathway for the problem reaction. So we broke down in two parts, first going from solid to liquid, and then from liquid to gas. So one big step was broken down in two small steps. So what I'm going to do is to draw the energy diagram for the small steps right next to the energy diagram of our reaction problem here. So let me change to red here. So we have a very tiny small step going from water in the solid state. Oops. To the liquid state. So that's the very first small step. And we also have the delta H. Oops. Which is plus 6 kilojoules per mole. And we also have the second small step going from liquid to gas. So now we have the second and final step going from liquid all the way to gas. And then here we have a delta H of plus 45.1 kilojoules per mole. All right, drawing the energy diagrams, can you see that the delta H of our reaction problem, water solid going all the way to water gas, is exactly the sum of the small first step and the second step, okay? So therefore, the delta H that we are looking for regarding the transformation solid to gas is exactly the delta H of solid to liquid plus the delta H from liquid to gas. That's what the Hess's law tells us. It doesn't matter the way you get from start to finish, because energy is a state function, okay? So we can, in this case, we broke down in two small steps, but you can break down in any amount of steps that you need to do it. The only condition is that you start from the same point and get to the desired point. So therefore here, we don't need to measure the delta H from solid to gas, but we need to know the delta H from solid to liquid and then liquid to gas. So let's get here the value of the delta H for the transformation from solid to gas. That's going to be the delta H of the first step plus the delta H of the second step, which give us here plus 51.1 kilojoules per mole. And that's how you use the Hess's law to determine the delta H of complex reactions from simpler reactions. A delta H of 51.1 kilojoules per mole for this specific reaction means that for each mole of water in the solid state moving directly to the gas state, we have to provide 51.1 kilojoules per mole to the system for the reaction to happen, okay? So therefore, we in the future will correlate amount of energy with amount of reagent or amount of product. Okay, so regarding here the units, kilojoules or kilojoules per mole are the most common units for delta H. It's just a matter how you show them. The most common one is just kilojoules, but when you have kilojoules per mole, then that means you are correlating directly the amount of energy for 1 mole of the reagent being transformed, okay? So while kilojoules is whatever amount you have for the stoichiometric coefficient. The divided by mole only indicates that you are talking about energy per 1 mole. Okay, so in this case, uh, it is a very simple case for Hess's law. What I would recommend you to do is to treat the chemical reactions as simple sort of mathematical equations. So that means you can flip reactions, multiply reactions, and cancel things that show up before and after the reaction. So for example, here, we can clearly see that what we are looking for is basically a sum of the first and second reaction. So if you treat both chemical reactions as mathematical equations, what you are going to have is H2O solid doesn't have anything to be added, so it will show up here at the end. However, water in the liquid state shows up as a product and as a reagent in the very next step. So therefore, you may cancel it. Okay, so everything that shows up after and before the next reaction can be canceled, and water in the gas state doesn't have anything to be added. And as you saw, the delta H is just going to be a sum of the individual delta H's. Okay, so therefore, kilojoules, 51.1 kilojoules per mole. So pay attention here. To cancel reagents and products, the physical state of the compound has to be the same. That's why I cannot cancel H2O in the solid state because it doesn't show up on the other side, but I can cancel water in the liquid state because it shows on the right side and then on the left side of the next equation. So treat chemical reactions as mathematical equations. Look at your reaction problem and the individual steps, and then we will arrange the chemical reactions to add up and get the final delta H. Remember, if we need to flip a chemical reaction, you can do that. The only condition is that the delta H has to change the sign, okay? If at some point you need to multiply a reaction by a factor, the delta H is also going to be multiplied by the same factor because energy is an intensive property. In other words, energy depends on the amount of substance that you have. Okay, so let's move to a more complex example here. We are looking for the delta H of the third reaction, chlorine reacting with ozone, producing chlorine monoxide and oxygen gas. Okay, so this reaction is a problem to measure the delta H, doesn't matter why. However, we can easily measure the delta H of ozone being transformed in oxygen, and then chlorine monoxide reacting with ozone, producing chlorine and oxygen. Okay, so these two reactions, the delta H can be easily measured. And what we are looking for here is the delta H for the third reaction. So let me rewrite the equations that we know the delta H here. So we know that the delta H for this first reaction is minus 29.9 kilojoules. And we also know the delta H for the second step. ozone producing oxygen gas. And here the delta H is plus 24.18 kilojoules. Okay, see here, Emmanuel, for this example here, we don't have kilojoules per mole, for example, for the second reaction. So that means you can correlate two ozone with the total energy here. If we had the delta H divided by mole, then the correlation would be for 1 mole of ozone and not 2. That is the biggest difference when you have the kilojoules versus kilojoules per mole unit. Okay, so the problem here is going to try to trick you a little bit. If you look at the first reaction, we have ozone being broken up in oxygen, and see here that the oxygen moves to the second reaction, reacts with chlorine and produces chlorine monoxide and ozone. So the first reaction is given to you flipped, because what we are looking for here is to produce chlorine monoxide, and chlorine monoxide shows up in the first reaction here as a reagent and not the product. Also, in the first reaction, we have Cl gas as a product, while the problem shows up Cl gas as a reagent. So that means the first reaction, we actually need to flip it. So what I like to do to solve these problems is to look at the problem reaction. So we see here chlorine gas as a reagent. And what's given to us is chlorine gas as a product. So let's adjust the first reaction here to reflect that chlorine gas needs to be a reagent. Therefore, what we are going to do is to flip the first reaction, chlorine gas plus 2 oxygen gas, producing chlorine monoxide and ozone. Flipping the first reaction, now we have chlorine gas as a reagent, and that matches what we are looking for. Also, we have chlorine monoxide as a product, which matches what we are looking for in the problem. Okay, so look at the problem reaction and look at the individual steps, and then flip or multiply the individual reactions to reflect what you were looking for. Now let's look at the second reaction and let's see if we need to flip it or not. For the second reaction, we have ozone as a reagent, and that matches what we have in the problem. In addition to that, we have oxygen as a product, matching what we are looking for. So therefore, the second step doesn't need to be changed because it's already reflecting the problem here. So let's repeat the second reaction. 2 ozone molecules producing 3 oxygen molecules. Now let's write the delta H's. Delta H for the first reaction is going to be plus 29.90 kilojoules. Pay attention to the fact that I flipped the first reaction. Therefore, the delta H sign has to be changed as well. That's the reason now we have plus 29.9. The second reaction, we didn't do anything with it, so it's going to keep the same sign and the same number for the delta H. Now we can add up both reactions. When we do that, we must find the reaction problem. Okay? Cl gas doesn't have anything to be added or canceled. So it's going to show up here. Pay attention to the physical state all the time. Now let's look at oxygen gas. In the first reaction, we have 2 oxygen gas molecules in the reagent side, while in the second reaction, we have 3 oxygen molecules on the product side. Treat the chemical reactions as a mathematical equation. If we have 2 on the left and 3 on the right, the net is 1 on the right. So therefore, after adding the 2 reactions, we will end up with 1 oxygen on the right side of the net equation. Now let's look here at chlorine monoxide, gas, nothing to be added or subtracted. So it will just show up as it is on the net reaction. And finally, ozone. We have 1 ozone molecule showing up on the right side of the first reaction and 2 ozone molecules showing up on the left side of the second reaction. So therefore, the net amount of ozone is 1 molecule on the left side. See here that after adding up these 2 equations, we have exactly the equation that we were looking for. It has to match. Therefore, the delta H that we find for the problem equation is going to be plus 29.9 plus 24.18, which gives us a plus of 54.08 kilojoules. And that's how you use the Hess's law to determine the delta H of complex reactions using small steps for individual reactions. Okay? So if you look here, in the first step, we are reacting chlorine with oxygen, producing chlorine monoxide and ozone. Ozone will react with itself, producing oxygen, and then this oxygen can moves up again, reacts with chlorine, and that's kind of a cycle. And the net reaction is chlorine gas reacting with ozone, producing chlorine monoxide and oxygen gas. Look at the problem reaction, look at the individual steps, flip or multiply the individual steps to reflect what you are looking for in the problem reaction. Remember, every time you flip a reaction, you change the delta H sign. If you need to multiply a reaction by a factor, the delta H is also going to be multiplied by the same factor. Okay. See here. All right. Change my screen really quick. Okay, so we are not going to have time to solve this problem today, but let's start it and I will give you the answer and you try afterwards. So this is where the Hess's law, it will get a little more complex, but if you use the same idea of looking at the problem reaction and try to match the individual steps to the problem reaction, you will be able to solve it. Consider the synthesis of propane C3H8, a gas used as camping fuel. So we can synthesize propane by reacting three molecules of carbon. Gr means carbon graphite. So we are going to see what's that on Friday. Okay, so three carbons in the graphite state reacting with four molecules of hydrogen in the gas state that will produce propane in the gas state. Measuring the delta H of this reaction is hard because it requires a lot of energy, so it is just complicated. It is difficult to measure the enthalpy change of this reaction. However, standard enthalpies of combustion reactions are easy to measure, and the problem tells you to calculate the standard enthalpy for this reaction here from the following experimental data. So we know that C3H8 reacting with oxygen, producing carbon dioxide and water. This has a delta H of minus 2220 kilojoules. We also know that carbon graphite reacting with oxygen, producing carbon dioxide, has a delta H of minus 394 kilojoules, and hydrogen plus half of oxygen producing water in the liquid state has a delta H of minus 286 kilojoules. From these three small chemical reactions, we must be able to find the delta H for the problem reaction. Okay, so let's look at the problem reaction and let's try to match the individual steps to the problem reaction. What I always look here is who are the reagents and who are the products, and I'm going to match each individual step to this reaction over here. So see here that we have propane as a product. Therefore, we have to match any individual step that shows propane with propane in the right side of the equation. The only reaction that shows propane is the first one. However, we see here propane in the left side, and we need to move it to the right side. So right out of the gate, I know that I have to flip this reaction to move propane from the left side to the right side. So that's the first thing you must do. When you flip, you also flip the sign of delta H. Let's look here regarding hydrogen. Hydrogen shows up on the left side. The only reaction that shows hydrogen here is the third one, and it is on the left side already. Let's keep this reaction as it is for now. And finally, carbon graphite. We only have carbon graphite in the second reaction. is already left side, and here left side. So for now, what we did was to flip the first reaction, keep the second reaction as it is, and the third reaction as it is. Before we add up reactions, we have to make sure the amount of each of the reagents and products is reflecting the amounts here in the problem reaction. Let's start with carbon graphite. We must have 3 molecules of carbon graphite. Our reaction only shows 1. To match these 2 reactions, what we are going to do here is to multiply the second reaction by 3. Okay, so we are going to add 3 here, 3 here. The whole reaction is going to be multiplied by 3, and the delta H is going to be multiplied by 3 as well. Okay, so rewrite this second reaction multiplied by 3 and the delta H multiplied by 3. Okay? So I'm trying to match what is showing up here with what needs to show up here. Finally, hydrogen. We need to have 4 hydrogens, and here in the third reaction, we just have 1. So therefore, to match the third reaction with the problem reaction, we multiply the whole reaction by 4 and the delta H by 4 as well. Okay, so now each individual step matches the problem reaction, and from there you just add them up. So recapping here, what we did was to flip the first reaction, moving propane from the left to the right side, matching the problem here. We just have 1 propane here, 1 propane here, nothing needs to be done. The second reaction we kept the same, however, we multiplied by 3 to match what you have in the problem. Don't forget to multiply the delta H by 3 as well. And finally, the fourth reaction, we did not flip because already shows hydrogen on the left side. However, we multiplied by 4 because it has to match the coefficient in the problem reaction. So multiply the whole thing by 4 and the delta H by 4 as well. Then after that, you just add up all the reactions. Anything that shows up on the left side and on the right side can be canceled, and you are going to get the net amount of the molecule at the end. Okay. Doing all those steps, we are going to get a delta H of minus 106 kilojoules, and that's the point where I will end for today. And we don't have in-class assignment this Friday, so I will see you on Friday for a regular lecture.
Thank you. Have a nice day.
Bye-bye.